Related rates are problems that have an equation with more than one variable, and then we take a derivative of the function, usually with respect to another variable such as time, and we have multiple rates in the same problem. Here's a problem solving strategy for doing these types of problems. First, draw a picture, name the variables and constants, and unless a variable is clearly made constant throughout the entire problem, we have to assume that it's a differentiable function of t and that there's going to be some change. So we have to take that into account. Number two, write down the numerical information in terms of variables you have chosen. Number three, write down what you are asked to find. Make sure that you understand what you're being asked to find. Number four, write an equation that relates these variables. You may have two or more equations that you have to combine. Then differentiate. Usually, again, it's with respect to time, and we're going to be implicitly differentiating. So think about it in that sense. And then finally, evaluate. When you evaluate, then you'll get the answer you need. Note that the expression must be left in terms of the variables that are changing before you take the derivative. A lot of times people want to substitute in numerical values that they have given in the problem, but those values are going to change at certain times unless, for example, there are some uh, some problems that have something that is clearly constant throughout the whole problem. But if that's the case, it's going to be told to you that it's constant throughout the whole problem. If it's not constant the entire time, you have to leave it as a variable when you take the derivative. If you don't, then you're probably going to get it wrong. So we have three examples on this video. Example one, a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. The cruiser is 3/5 of a mile north of the intersection, and the car is 4/5 of a mile to the east. And the police determine that the distance between them and the car is increasing at a speed of 20 miles an hour. If the cruiser is moving at 60 miles an hour at the instant of the measurement, what is the speed of the car at the same time? Fortunately, we already have a picture for this problem with helpful, it looks like a baby or something that is driving this car. But we want to find out the speed of the car. So, what we're actually trying to find here is the rate of the car, and we're given a bunch of information. So, if I call this x, um, the distance that the car has traveled east, and y, the distance away from the intersection that the police cruiser is traveling south, um, what or the distance that the cruiser has to travel south, we have certain information. We know that x is zero point 0.8 miles from the intersect, or x is zero point 0.8 miles from the intersection, so it's gone 8/10 or 4/5 of a mile. Y is 0.6 miles, and then we can use the Pythagorean theorem to figure out what the distance is. So since we know that x squared plus y squared equals d squared, I'm making d the distance between the two cars. I know that 0.8 squared plus zero point 0.6 squared equals 1 squared, just using the Pythagorean theorem and solving for d. So d equals 1 mile. So now there's some other information that we were given. We were given that the distance between them and the car at that moment is increasing, or the distance between them and the car is increasing at a speed of 20 miles an hour. So that means the derivative of the distance with respect to time is 20 miles per hour. The other thing that we know is that the car, or the cruiser, so that's y, is moving at 60 miles an hour. One thing that's important to note is that the cruiser is moving south, which in this picture is going to make this part of the triangle smaller. And because it's making that part of the triangle smaller, this is actually going to be a negative 60 miles an hour in the sense of what's actually happening to our picture. And so um, it's not going to increase the distance, it's going to decrease the distance. So basically what's happening is we have this car moving to the right and increasing the distance. We have this police cruiser moving down and decreasing the distance, and we're trying to figure out what what the rate of change or the speed of the car is because we have two other pieces of information. So I'm going to use the Pythagorean theorem that I have, which is x squared plus y squared equals d squared, and then I'm going to take the derivative of this. Now think implicit differentiation, so 2x dx dt plus 2y dy dt equals 2d dd dt. And at this point, you think maybe we could have picked a different letter for d for the distance, but it is what it is. So if we are taking a look at the information that we have, one thing that is important to note in this problem is that I have 2's everywhere. That means I can divide the whole equation by 2 and actually make the problem a little bit easier to calculate, since this is probably a no calculator problem. So x dx dt plus y dy dt equals d dd dt. Now I just start substituting values in that I know. So x equals 0.8. dx dt is what we are trying to find, because that's the speed of the car. Y is 0.6. dy dt is 60 miles an hour in the negative direction. And then d is 1, and dd dt is 20, because that distance is increasing. So that means it's going to be a positive 20. So we end up solving this. So I get 0.8 dx dt minus 36 equals 20. I add 36 to both sides and divide by 0.8, and I get dx dt equals 56 divided by 0.8, which is 70 miles per hour. So notice that makes sense. If the cruiser is moving at 60 miles an hour this way, and this is increasing, it's possible that the car is moving a little bit slower than the cruiser, but considering how much the distance, the rate of the distance is increasing, at that point in time, you would think that the car is moving faster than the police cruiser. So the police cruiser is moving at 60 miles an hour, and the car is moving at 70 miles an hour. Also notice I didn't substitute in 0.8, 0.6, and 1 into the Pythagorean theorem when I took the derivative. That's because all three of those things are going to be changing. It doesn't give us any indication that any of those are constant. A spherical ice ball is melting at a rate of 8 milliliters per minute. We're going to note that milliliters is the same thing as centimeters cubed. How fast is the outer surface area of the ball decreasing when the outer diameter is 20 centimeters? So let's draw a ball. The radius is r. Some information I have. The volume is changing at 8 milliliters or centimeters cubed per minute. Notice that it is decreasing or melting, so that means we're going to put a negative sign there. The other thing that we know is that the radius is 10 centimeters. I'm given that since the diameter is 20, and then I'm going to convert it to r just to make my problem a little bit easier. So now what I want to do is I want to write down the formula for the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. Notice that the volume is going to be changing since it's melting, and the radius is going to be changing since it's melting, so I can't substitute anything in before I take the derivative. Also notice that I am going to need to know geometry formulas in order to do these things. So I know that the formula for the volume of a sphere is 4/3 pi r cubed. I know that the surface area of a sphere is 4 pi r squared. These are things that I have to know. I have to know the volume formulas and surface area formulas of cylinders and cones. These are things that I have to know in order to be able to do these problems, and they will not likely be given to you on any AP problem. So you will have to know these formulas from geometry. Now I take the derivative, dv dt equals 4 pi r squared dr dt. And now I can start substituting values in. So dv dt is -8, r is 10, and then I solve for dr dt. So I divide, and I get -8 over 400 pi is equal to dr dt. And I'm going to simplify that, make it -1 over 50 pi is dr dt. That actually does not give me my answer because it's asking about the outer surface area. So that means I need to take into account what the surface area is. So the surface area of a sphere is 4 pi r squared. Notice that I started with the formula for volume because they gave me the rate of change of the volume. But now I have to actually get into how do I find the rate of change of the surface area. So now I have surface area equals 4 pi r squared. I'm going to take the derivative of the surface area. I'll make it dSA because I defined it as SA already. So dSA over dt is 8 pi r dr dt. And now I can solve for the derivative of the surface area by just substituting values in. So 8 pi times 10, since the radius is 10 at this point, times -1 over 50 pi. Notice that this is basically 80 pi and this is 50 pi. So that ends up being -8/5. The pi's cancel out, which is -1.6. So the rate of change of the surface area with respect to time is -1.6 centimeters squared per second, or per minute, sorry. And that's my final answer for this problem. If we recognized that 4 pi r squared was the surface area, maybe we could have done some stuff there, but it would have been relatively challenging to do that. Problem 3. A particle moves along the parabola y equals x squared in the first quadrant in such a way that its x-coordinate in meters changes at a constant rate of 10 meters per second. How fast is the angle of inclination, theta, of the line joining the particle to the origin changing when x equals 3? Let's take a look at what this actually would look like. So here's the parabola y equals x squared. I'm going to have this point trace a point on the parabola. And then what we're looking at is we're looking at the angle that's being formed by my mouse and the rate of change that that is increasing. So we're kind of looking at how fast that angle is moving. Notice what we can do is probably make some sort of right triangle and figure something out from there. And my microphone just got caught on a table and that kind of hurt my head. So let's take a look at what's going on in this problem. I'll draw 3 pictures and hopefully the 3 pictures will help us a little bit. So the first picture is just going to be y equals x squared. And when I'm at 3, I don't know why I just made that a point. So when I'm at 3, the y value is 9. But notice that this, again, is not something that's going to be constant. This is changing. So I want to keep these in terms of x and y, and then just remember that it's going to be 3 and 9. So then, if I make another picture, what I might want to note about this picture is that this triangle is actually occurring in this picture. And so because that triangle is occurring, I'm going to copy that triangle. And then if I have this point x comma y, I'm trying to find theta. And so if I try to find a theta in this, I'm going to use what I actually know. So if that's theta and x is 3 and y is 9, I can do the Pythagorean theorem and get the square root of 90 at this exact moment. And then I'm going to use tangent. So remember, these are actually y and x, and they're not staying the same. at this particular time. They're changing. This point is moving at a constant rate. So I know that dx dt in this problem is 10 meters per second. And then I have x is 3 at the moment that I'm actually talking about. So I can take tangent of theta is equal to y over x, but note that y equals x squared in this problem. So because y equals x squared, we're talking about this parabola. Since y equals x squared, I can replace y with x squared. So I have tangent of theta equals x squared over x, which means that tangent of theta is equal to just x. So now I have a function that I can take the derivative of. So tangent of theta, when I take the derivative, that's secant squared theta, d theta dt, and that's equal to the derivative of x, which is just 1, dx dt. Now I'm going to substitute some values in. So dx dt is 10. D theta dt is what I'm trying to find. And secant squared of theta, well, theta at this exact moment is some kind of number. But what I can do is I can replace secant, because I know secant is r over x. So I know that that's root 90 over 3. So I have root 90 over 3 replaces secant. And then I'm going to square that. So now I have 90 over 9, which is the same thing as 10, d theta dt equals 10. So if I have 10 d theta dt equals 10, that means that d theta dt is equal to 1 radian per second.